Okay, so welcome everybody. I'm Gabor Horvath, and I will talk about static analysis using Clang tools. I'm a PhD student working on static analysis and program language design research. And let's see what will we talk about this time. I will introduce you what static analysis is, why should you use it, why it is a hard problem in general, and I will introduce you briefly with some of the algorithms that some of the static analysis tools are using, and present you some of the open source tools that you should definitely try out because they are very useful, and also show you how should you approach to best use these tools, how to integrate these into your workflow. And finally, if we will have time, I will talk about how to write static analysis-friendly code, which is very useful because sometimes when you write static analysis-friendly code, that also happens to be cleaner and easier to understand. So sometimes code that is easier to understand, the static analysis tools are also easier to understand to other people. So it is also good for code comprehension. Static analysis is basically analyzing the code without executing it. This is a very broad topic, and it has a wide variety of use cases. For example, when the compiler reasons about the code, what optimizations are safe, what optimizations are not, that is also static analysis. We can use it to do code transformation, verification, visualization. But during this talk, every time when I mention static analysis, I will think about a tool that can help us to find bugs in industrial code bases. Or not necessarily bugs, sometimes code smells, fragile code, or code that should be rewritten to improve some of its properties. It's not necessarily correctness, it can be performance or anything similar. When we are reading code, and we try to reason about it, we try to answer some of the questions. Then we are basically doing static analysis manually. So tools sometimes employ very similar assumptions about the code that we do when we are reading it. Unfortunately, static analysis is a very hard problem. Probably you are familiar with the halting problem. When we have a basic question like, does this program terminate if I give it a certain input, is undecidable algorithmically. So it is a very strong property of reasoning about programs in general. And according to Rice's theorem, every interesting question about the program is undecidable. Let's look at this simple code snippet I have here. We might be wondering whether the value of the variable x might be changed during the execution of this program. But in order to be able to tell this, we need to solve the halting problem, which is undecidable. So even this question, does the value of this variable change, is undecidable. So we cannot solve undecidable problems, of course. So as good engineers, what do? We employ approximations, we employ heuristics. So this way we can get useful results. Of course, there is a cost to that, because this way there are some false positives when we report some diagnostic for an issue that does not exist. And there might be also false negatives when we miss some real errors. When we do verification, we would like to eliminate all of the false negatives. However, when we are trying to use these tools in the industry, in not a safety critical code, but in a setting that we want to reduce the cost of software maintenance, then we would like to reduce the false positives, because we do not want to waste the precious developer time on reading false positive results. We want to spend the time to fix bugs. So why should we use static analysis in the first place? Well, one of the best properties of static analysis is that no code execution is required. So it also works when we have very little or no test coverage, and also works when the runtime environment is not available, or it is very expensive to actually run the program for some reasons. And there are also some properties that are very hard to write a test for. For example, you cannot write a unit test or integration test to verify coding guidelines or other, and there are other similar properties as well. You cannot write a test to catch certain kinds of undefined behavior because it's undefined behavior, so there is no, in some cases there is no certain way to detect that. So we can use these tools to overcome some of these issues. We can enforce coding guidelines more rigorously, and it is also a very cheap supplement to testing. The earlier we detect a bug, the cheaper to fix it, because when we are able to detect it while we are looking at that code, we have all the information in our working memory, so we can pretty easily fix that. If we catch it later, then maybe the bug is assigned to another developer who have never seen that piece of code before. So it will take more time to fix it, and also more time to fix it means it is more expensive for the company. And also, in case the bug is not found at all and it causes some problems to the clients, then it is even more expensive. So static analysis is hard, but it definitely works to do it. Unfortunately, analyzing C++ is even harder. One of the main reasons is the compilation model, because the way headers work, we need to reparse a lot, and eventually modules will be able to come to the rescue, but that's still a long road to that point when we have modules deployed in most of the industrial code bases, so we cannot really rely on that right now. And also, it is very hard to parse C++. We can't even lex C++, for example, without knowing the template names properly. And also, we need type information to parse, to solve the ambiguities in the C++ grammar. For example, in the piece of code snippet that you see, in the first line, unless we know that what the uppercase T is, we cannot be sure whether this is actually a multiplication or a pointer declaration, definition. On the next slide, we cannot be sure whether this is a function call or a declaration. And on the last line, we cannot be sure whether this is the reference of a pointer followed by a cast or a multiplication. So when we do not have the type information, then we basically cannot parse the code. So the semantic analysis, the syntactic analysis, and even the lexing to some extent is coupled very strongly when we are writing tools for C++. And also we cannot really just solve the problem of the compilation model, because macros make it hard to cache the representations of header files. Okay, so let's look at some of the methods that some open source tools are using for static analysis. One of the easiest way to do some basic analysis is to do textual pattern matching. I'm sure that all of you already done this. For example, when you wrote a little grep command or something like that. And CPP check also able to do this kind of analysis. It first transforms the code to some canonical form, so you do not have to deal with too many cases when you write the patterns. And there is a relatively easy way to find trivial division by zero errors using, for example, when we are looking for division followed by the literal zero. However, we cannot find more complicated cases where we would need to do some more deep analysis, for example, data flow analysis or something like that. So it has a lot of disadvantages, but it is relatively easy to implement. It is fast, but we have very little information available. We can also match the syntax tree of the program instead of the textual representation. And when we are matching the syntax tree, which is an intermediate representation of the compiler, we have much more information available because the compiler already did a lot of job for us. It deduced the types, it resolved the type defs, and did a lot of hard work. So we might be able to find, in this case, that the user messed this malloc up because she wanted to allocate the memory for a double, but instead she allocated the memory for a pointer. And the size of a pointer and the size of a double is might not be the same. And this is, in particular, an error that it is very hard to write a test for. In case in your platforms, these two types happens to be the same size. So this is one example that it is easier to catch using static analysis than writing tests. Let's look at a more advanced analysis. Let's look at a flow-sensitive algorithm when we would like to find division by zero errors. In flow-sensitive algorithms, we do walk on the control flow graph. For example, here we know initially the value of variable x, and then there is a condition, so we split the execution pads, and in one of the branches, the value of x is no longer 0. On the other branch, it remains to be 0 when the branch is not taken. So the question is what to do when we merge these two execution pads, and basically we can define the lattice. So depending on what kind of analysis are we interested in, we can define the rules what to do at merge points. In this case, we would like to get the minimal element at each merge point. So we will conclude that when these two pads merges, then the value of x might be 0. And then when we split at the next branch, we will report that there is a division by zero error, and it is a false positive error because in this case these two branches, these two conditions are correlated, and every time when we divide by x it cannot be 0. So using this algorithm we will end up having a false positive. Let's try to fix this. So let's do the analysis again, but this time let's try a different lattice. In this different lattice, we will conclude that the value of x is non-zero, so we will not detect any division by zero errors, but in this case, the two conditions are correlated in a different way. So when we're using this lattice, we will miss a real division by zero error. So in this case, we have a false negative report. So it looks like no matter how we define the lattice, with this kind of analysis, we will always have either false negative or false positive results. But this algorithm is very efficient. So let's try something even more advanced. So let's try a pass-sensitive algorithm. So the problem was that when we merge two pads, then we cannot know, we lose information, basically. And we do not want to lose information, so in a pass-sensitive algorithm, we keep all the separate pads, we never do a merge, we let these execution pads to explode, basically, and we try to do a simulated execution. So when we are trying to enumerate every possible execution pads, we try to do something like an interpreter, which interprets the meaning of our code. It is almost like running it, but we do not expect the inputs from the user. We do not expect inputs from files or over the network. But instead, when we encounter a value that we know nothing about because it was supposed to be given by the user, for example, we represent this value using a symbol. And during the execution of a certain execution pass, we record the information that we have about that symbol from the conditions, and we can also prune impossible paths. The execution time of this algorithm is exponential in the branching factor, but using some clever techniques, it might be feasible to use this on real-world code bases. So let's look at an example how this symbolic execution works. There is a piece of code, and when we try to execute symbolically this function, we try to interpret it. At first, we have no information what the value of the variable b is, so we represent this as a symbol. There is an uninteresting branch there, where the value of b can be anything but 1 or 4, and nothing interesting happens in this case. There is a case where the value of b is known to be 1, and in this case, we can very easily detect the division by 0 error. And the most interesting case in this example, when we know that exactly the value of b, the symbol, must be 4, therefore, we can compute that the value of c must be 0, so we can catch the division by 0. So when we are doing this symbolic execution, we are representing the program states as nodes in a graph, and every edge is a state transition. And while we are interpreting the code, we are generating new states using these state transitions, and each time we try to determine whether that state is valid or not, and when we find an invalid state, then we report an error. I showed you the rough idea how to model the values. However, C and C++ is not just about the values. There is a whole lot more going on while we are executing programs. We have to reason about memory. We might be interested about aliasing, how the memory hierarchy looks like, what about the memory locality. And there are also ways to model this information. For example, we can model it hierarchically, that a certain piece of memory is on the stack within an array, within an element of an array, and within a field of that element. And this way we have a lot of information about how the memory layout might look like without trying to assign exact locations to these memory regions. It is also interesting to talk about context sensitivity when we talk about interprocedural analysis. So when our analysis can reason about the code across function calls, then we might be interested in whether the analysis can evaluate the function with respect to the calling context. So in this case, in the calling context, the getNull function is called with the value 5. Therefore, we can conclude that it returns the value 0, so we can find the division by 0 if we have context sensitivity. It is also important to try to reason about the code across not just function boundaries, but also across translation unit boundaries. In this example, when we first call the function f, which is defined in a separate translation unit, we know that the value that was pointed by the pointer x is positive because of the condition. But since we have no information about the function f while we analyzing the a.cpp and the corresponding translation unit, and the function f could do anything to the value that is pointed by this pointer, we have no information about the value pointed by x by the time we call the function f the second time. So when we have a function, we call a function that we have no information about, we have to do some conservative approximations to avoid concluding unsound results. And this way, the information that we gathered during the symbolic execution can be lost, which can have a very bad result in some certain circumstances. And in case we have cross-translation unit analysis, then it is even better to have global analysis when we do not only talk about analyzing across translation unit boundaries, but also analyzing across projects and libraries. And it is also a hard question, how can we analyze across projects when one of the project is actually closed source, so we do not have access to the source code. So it is very likely that we will always have some kind of boundary where we need to encounter some unknowns, not just about values, but also about the call graph or the layout of the memory or the shape of the heap. So every time we design an analysis, we have to think about what will happen when we do not know some very important information because of a call to some unknown code. Those are very frequently used technique to do interprocedural analysis is summary-based analysis. So one way to analyze function calls are to basically each time when we encounter a function call, do what an interpreter would have done, reanalyze the body of the function with respect to the calling context. Another way to do it is to first analyze all of the functions and assign some information about the function to each function. So this is called summarization, and instead of emulating the function call, use the summarized information to get some conclusion about the code. So let's talk about some of the open source tools. I think you might have guessed from the title of this talk that I will talk about the Clang related ones. So the Clang static analyzer is a path-sensitive analyzer. It does symbolic execution. It has very good memory modeling capabilities, and it is context-sensitive. So it does very, very deep analysis. It can catch a lot of bugs. Unfortunately, right now, it lacks cross-translation unit analysis support, but the community is working on it, so it might come sooner or later. The Clang tidy supports code rewriting, so it's not just a bug finding tool, but it is also a refactoring tool. It has large amount of checks and it is growing very fast. So if you look at the release notes of each release of Clang tidy, you can see that there are more and more checkers are coming in each release. So it is getting momentum really fast. It doesn't do very deep analysis. Most of the checks are based on syntax tree matching, but even though the analysis is not that deep, some of those checks are very, very useful, and they are also very reliable. It also lacks cross-translation unit analysis support, and there are a lot of useful checks for the C++ core guidelines or Boost, or there are also code modernization checks, so it can convert some of the loops to range-based for loop, for instance. So in case you have a code base that was written with an older C++ standard, then Clang tidy can help you a lot modernizing it. And also, there are a lot of best practices implemented as checks. So you do not need to always keep in mind all of those best practices, keep them in your working memory. Clang tidy can remind you that you should do this something in a slightly different way. And I think it is very useful. It can help us to have less cognitive overhead while we are doing development. So how should we integrate those tools into our workflow? Well, in case we have an old and huge project, then it might seem like an impossible challenge to actually fix all the reports or suppress all the reports or triage them that is reported by those tools. And the only strategy that we could take is to fix the most important defects gradually. In greenfield projects, it's much easier. We just need to keep the number of reports minimal, ideally 0. So one of the first actions that we would like to do is to integrate these static analysis tools into our CI, or continuous integrations, loops. And for example, one of the technique that is used by Facebook is each time when somebody submits a commit, then an automatic code review is initiated. And in this code review, when one of the analyzer is found one of some errors, then it is posted to that code review. So the committer can react to that. He can either say that it is a false positive or rewrite the code to pass the analysis. So it can make it much easier to deal with those tools. It is important to support incremental analysis locally on your machine, because some of these software actually take longer to run than a compilation, so you do not want to wait for this tool to reanalyze all of your project files every time when you want to commit something. But if you have a CI loop, then you probably want to have a full analysis on the nightly builds. When you have a report from a tool, you need to triage it, whether it is a critical or a non-critical issue, false positive, did you fix it yet, or something like that. And you should be able to mark false positives in a way that when you rerun the same analysis, this report that you marked as false positive will not reappear. And also it is useful to skip uninteresting files because it is maintained by others, or it is a third-party library, and it is better when the tool that you are using is easy to use. There is an open source project called CODECHECKER, which is a tool to integrate Clang tidy and Clang static analysis into your workflow. It is actively developed by Ericsson and might end up under the LLVM umbrella. And right now it supports Mac and Linux. I don't know when will the Windows support is coming. And in case you are interested in how the architecture of this software works, there is a Euro LLVM talk that you should check out. So CODECHECKER is basically a web viewer for the facts. So the results of the static analyzer and the Clang tidy can be viewed using your web browser. And you can also do filtering. So you can write certain queries. What kind of reports are you interested in? And also you can mark bugs as false positives, so they will not reappear when you are reanalyzing your project. There is also a differential view, so you can compare two analysis runs of your projects, for example, a version from yesterday and a version from today, and you can check which new issues were introduced compared to the baseline from yesterday. And it also supports incremental analysis and makes it easier to integrate these tools into your build system. It can be integrated into the CI loop using command line tools or into Eclipse and into Code Compass, which is a tool to help you read the code. So it's basically a code comprehension tool, and I definitely recommend you to check it out. The usage is relatively easy. There is so basically, if you have a project that needs to be checked, and it is using auto tools or CMake or basically any other build system that is available in the open source community, you can just give the name of this check and then give the CODECHECKER the command that you usually use to build the project, and then when the analysis is finished, there is a command to start the web server, and then you can view the results using the web browser. There are some screenshots of the user interface, and it tries to explain you how can the bug it found be reproduced. So it not just shows you the diagnostic itself, but also show you the execution path on which this report was detected. There are some easy to remember rules how should you use. When you have a unique name for a check, then you should recheck the whole project. And when you do incremental analysis, then you should reuse a check that you used earlier. And the web viewer is localhost only by default for security reasons. So in case you want to run this web server on the CI machine or something like that, then you need to pass an extra flag to enable remote remote clients to connect to the server. And for baseline view, for differential view, you should select the baseline first. So finally, let's talk about how to write static analysis code and why do you want to write static analysis code in the first place. So one of the best way to make your code static analysis friendly is to minimize macro use, because refactoring tools like Clang tidy cannot rewrite code safely that is the result of some macro expansion. So it is, so if you want your code easy to be transformed, then it is good to minimize the macro use, and you might also get code that it is easier to understand. You should avoid non-standard extensions because some tools do not support them. And your first line of defense is always the compiler. So the first step to be static analysis friendly is to fix the compiler warnings. It is good if you have a type-rich program. Using a type-rich programming in a type-rich way can also help to have the compiler to produce code that is more performant. For example, type-based alias analysis can help the compiler generate faster code. And also, in case you can guarantee some safety property of the program using the type system, do so, because the type checker is your most useful static analysis tool. It is sound, and if you can guarantee that some classes of errors do not compile, then those classes of errors cannot occur at runtime. Do not overuse references or pointers. Try to avoid global variables. It is important because then these tools do not have to reason about aliases that much. And also, reasoning about global variables needs global knowledge. So if you have fewer global variables, then it is easier for the tools to reason about your code, and it's also easier to your coworkers to reason about the code. It is useful to encode as much intent into your source code as possible, and one of the ways to do that is to use annotations. Those annotations are great and can convey a lot of additional information about the code and what you want it to do. And they can also provide the static analysis tools with very useful information. One of the most important things to annotate is the custom assertion functions that you might have. I will show you shortly why. And also, if you are the author of a library, then annotating the functions in the library will give these benefits to all of the library users. So use annotations if you are a library developer. It is always useful to analyze the debug build, because in debug build, asserts are not compiled away, and those asserts can also convey useful information about the invariance of your code to the static analysis tools. And if you are using build systems that almost nobody knows about, then you will have a harder time to get support for integrating the static analysis tools into your workflow. So let's look at why it is important to annotate custom assert functions. In this code, the user wanted to assert that the value of this pointer is never null. Unfortunately, what the analyzer can see right now is that there is an inconsistency in this code such that the author did consider the case that the value of this pointer might be null, and then he dereferenced this pointer in a branch that is not guarded by the check. So in case we tell the analyzer this custom assert function is a no return function, then the analyzer will know that it can never happen. Such case can never happen when we are dereferencing a null pointer. Okay, so one of the most important things when we are dealing with static analysis is how do we handle false positives. First, let's think about what can be the reason that we can find false positive reports. One of the possibilities that the analyzer couldn't prove that an execution path is impassable, and each report that is found on an impassable path is a false positive. Or there is some information about our code that is unknown to the analyzer. It couldn't infer that from the code. So the best way to actually fix this is to have the analyzer understand our code. We cannot assert or rewrite code snippets in a more easy to understand way. We can use widely used APIs instead of custom solutions. So these changes can also help readability, and in case we make our code more readable, we can also decrease the maintenance cost of the software significantly, because if you think about it, most of the time we spend most of our time actually reading code and not writing it. So one of the important pieces for the Clang static analyzer: do not turn off core checkers to suppress warnings. The reason is that core checkers are not there only for reporting warnings, but also there for modeling some aspects of the code, and it is unsupported to run the Clang static analyzer with those checkers turned off. It might crash or give you garbage results. And also, there is a possibility to exclude some of the problematic code from the static analysis using macros. As a last resort, we might mark a report as a false positive, but in each case we mark something as false positive, we need to be very pedantic. We need to comment, why is it a false positive? Why is it not possible to change the code that it is easier to understand? What are the requirements to remove this suppression? Is it something that I need to change the code, or is it a bug in the analyzer? It might be good to add a link to the bug report in the static analyzer, so we can know that when can we remove this suppression. And also, some of the tools are trying to not to report errors that are in system headers. So some people are marking headers that are third-party headers as system headers. So the analysis tools do not report them. Do not report the errors that found in those headers. That might work in the short term, but in some cases the analyzers treats functions that coming from system headers differently. So in some cases you might introduce false positives or false negatives when you are doing this. So to conclude this talk, static analysis is very useful to have in your workflow, and there are plenty of powerful tools available for free. And writing static analysis friendly code requires some effort, but it is worth it, because most of the times it also helps you to make your code more readable. And if you are a library developer, you should pay extra attention to those static analysis tools, because if you make your code static analysis friendly, all of your users can profit from that. And your clients might be interested in static analysis, even though if you are not. And there are some references for some of the talks and tools I mentioned. So thank you for your attention, and in case you have some questions, I will try to answer that.
Yeah, any questions?
Hi. What is the support for the C++ core guidelines you are aware of in the today's Clang static analyzer?
So can you repeat the question? What is the support of? I didn't catch the...
Yeah, so for example, if I use a Clang static analyzer today, do I have support for the C++ core guidelines or Clang tidy?
Oh, so what is the support of core guidelines? So it's I did not compare it to other tools, but it is definitely some gap between the core guidelines and the implemented checks. So there are a lot of work to do, but it is improving, and I would expect that if you would like to introduce or you would like to follow the core guidelines, it would be worth to use Clang tidy as soon as possible, because you can first fix those errors or those violations of the guidelines that the Clang tidy can find now. And with newer versions, newer checks will be available. So this way you can introduce the rules of the guidelines gradually into your project. So it is not an initial big work, but you have always some time to fix those violations.
More questions? If nobody has a question, I have a question. When will Clang tidy support Windows?
I think Clang tidy is supporting Windows right now, and Clang static analyzer as well. So the CODECHECKER tool that I introduced is the one that is not supporting Windows at the moment, but it is possible to run both Clang tidy and Clang static analyzer on Windows, but you might be able to find some bugs because it's not tested that extensively, and there are fewer tools to help you integrate into your build environment.
Yeah, come on, more questions.
Yeah, but can we turn the question around? What is the best code analyzer to integrate in Windows? For example, on the TFS vNext build platform.
So on which platform?
On Windows. When do you run this TFS build? I think it's called vNext, the latest 2015. What is the best static analyzer tool for to run at that sort of build system?
I think with static analyzer tools, it is always the more you try, the better, because most of the tools are not supporting the same. There are no subsetting between one of the tools and the other, but there are always some of the rules that is supported by one tool and not supported by other. So it is really hard to really hard to say that which tool is the one that you should use. The more tool you use, the better. And how should you integrate that into your, for example, Visual Studio project? In case of Clang tools play pretty well with CMake, and with the newest versions of Visual Studio supporting CMake, I think it will be easier to use those tools on Windows.
So the more tools, the better. I think Clang tidy includes the Clang static analyzer checks also. Do we need to run both of them or just Clang tidy?
Okay, so the question is, with Clang tidy, you can run the Clang static analyzer as well. Should we run both of them? I think we should run both of them. And the reason is when you are running the Clang static analyzer using the Clang tidy binary, then you get the textual report, which does not include the path information. Where did the bug occur? So in case you want to have a detailed report that gives you better user experience, then you better off running the Clang static analyzer separately. And then it will generate some plist files that can be imported into other tools like CodeCheckер or Xcode or Qt Creator. So basically, I would recommend running the Clang static analyzer separately.
Hi. When you were talking about false positives and handling false positives, you said, or you urged us to not turn off the static analysis, but to pre-process the code. What exactly did you mean by that, or what can I do in these cases?
I think I did not mention that, but it was on the slides. So when I say pre-processing, I wouldn't mean pre-processing the code, but pre-processing the reports. So the reports that are not relevant to you are not displayed to the user.
Okay.
Thank you for the question. Okay.
Hello. I know there is a special version of Clang to integrate into Visual Studio, and they are the snapshot builds of Clang. How do the static analysis tools need special support for compiling or analyzing Windows code? Is there any connection between what Clang does, special emulating Visual Studio compiler, or is it not necessary?
So basically, I think the front end that is used by the version that is distributed by Microsoft is the same, or have very minimal very minimal changes compared to the open source version. So the Clang static analyzer should work in that version as well, but I did not try it. And so basically, because the standard library, especially the C standard library used by Windows, is a bit different than the one that used on other platforms. There might be cases where the Clang static analyzer is not that precise on Windows than on Linux or Mac, but more and more people started to use these tools on Windows as well, so it is catching up pretty quickly. So I think even if there are some differences, they will be fixed very soon.
Any more questions? Okay, then thank you for answering all the questions and a good talk.
Thank you for your attention.